I never have enough time, always rushing around.
You seem to be really busy all the time and you just don't know where it goes.
Everyone struggles to get to places on time. But that's nothing compared with the journey science has taken to understand time itself. Once you've taken that trip, you never look at your watch in the same way again. Even though it's early, I'm already late. We all live our lives counting the minutes and seconds of a universal clock. Your time is the same as my time. It's the absolute thing against which we measure our lives.
Time is what we perceive to be happening around us. Time is the structure that people use to define an interval.
We see time as flowing uniformly, like a uniformly flowing river. And furthermore, we see time as actually flowing at exactly the same rate for everybody. And that's the way Newton saw it. He called it absolute time.
But the truth is much more bizarre than that. In 1919, the world became aware of extraordinary new ideas about the way the universe works. Time is unique for every one of us. Your time really is different to mine. If I move very fast, you'd see my time slow down. The higher I get, the faster my time goes compared with time on the ground. Time had a beginning, and it might have an end. This is the story of the life of time, from where it began to where it might be going, and some of the strange bits in between. It's a journey through the ideas that made an unknown patent clerk into the most famous scientist of the 20th century.
He had the courage to defy Newton. Newton was this great towering figure in the history of science. And he was able to defy Newton, and he was able to say things which were sacrosanct to everyone else. Space and time could change, and that was his genius.
From special relativity to general relativity, Einstein produced a revolutionary theory for how time works. Perhaps the most remarkable prediction was that time hasn't been around forever. Just like a race, it started with a bang.
Big Bang was like the blinding fireball of a nuclear explosion. And as the universe expanded after the Big Bang, it cooled. And as it cooled, things began to sort of condense out of it. Things began to congeal. First we got the building blocks of atoms, and then they combined to make atoms themselves. That actually occurred about 300,000 years after the Big Bang. And eventually, those atoms clumped together to make stars, the first stars, and those stars clumped together to make the galaxies. And we live in the Milky Way galaxy, which is just one of 10 billion galaxies flying apart in the aftermath of this gigantic explosion.
So if they're so clever, what happened before the Big Bang?
The Big Bang was really the start of space and time. When the Big Bang occurred and you got the creation of space, you also get the creation of time. So the question, the classic question, what was there before the Big Bang, is actually quite meaningless.
I think most people have the misconception that that was like the explosion of a lump of something in some pre-existing void, that there was always some space there and always time, and that at some particular moment, bang, you know, off it went. But that's not at all how it is supposed to be.
To ask what there was before the Big Bang is a ridiculous question, because there was no before. There was no time to embed the word before in.
Before the Big Bang, no time.
No time before the Big Bang?
No space, no nothing.
Absolutely nothing?
Well, we don't know. No one knows. What could have been there?
Nothing.
Yeah.
Time began at the Big Bang. That was the edge of time.
Only after a short time, which was quite short, a very small fraction of a second, did the laws of physics as we talk about them today come into play.
Once time got started, you might think it just runs along like clockwork.
that there's one absolute time we can all agree on. Isaac Newton thought so, and in everyday life it's more or less true. But Albert Einstein said something remarkable, revolutionary.
He said speed slows down time.
Your time and my time can get out of step in a very simple way. If I were to just get up and wander around this room, for example, then there would be a very slight mismatch in the, if you like, the rate at which my time and your time progressed. So if I carried a clock with me, which was very accurate, and we synchronize clocks before I wander about, and then when I sit down again we compare, there'd be a very slight discrepancy between us. So time is something which depends upon your state of motion, and that's something that can be directly demonstrated with experiment.
Imagine Chris could run at a constant speed, close to the speed of light. Then some strange things start happening.
If, for instance, an athlete were to run at a speed that was close to the speed of light, then they wouldn't experience anything different. But for someone watching them zoom past, they would see, first of all, that if they were carrying a stopwatch with them, that was ticking by more slowly. So time was going by more slowly for the moving athlete.
This is the key point. If you only remember one thing about special relativity, remember this. Time actually goes slower for someone who's running at a constant speed relative to someone else.
That relative thing is very important. For Chris, time is running at a normal rate.
But I see his time going slowly.
Sounds odd?
But time slowing down is a real, measurable effect.
In 1971, two scientists flew around the world carrying incredibly accurate atomic clocks. When they returned to Earth, they found that time really had slowed down for their clocks in comparison with ones left on the ground. But it's such a vanishingly small effect, we don't notice it.
This effect is very small. We're talking about tiny fractions of a second. However, if it was possible to travel near the speed of light, this effect would be very marked indeed.
Because Chris is moving relative to me, I see his time moving more slowly. But how does Chris see my time?
The interesting thing is if the person running looked at you, they would see your time slowing down as well. This process is completely symmetric, and that is why it's called relativity. You would also be moving at high speed according to the athlete, and so all these relativistic effects would occur for you as well.
Have you got the time? Because, I mean,
Well,
you see, it's relative. You see, your time
My time is relative.
is relative to you. It's not, you see, it's different to me.
So we don't have the same time?
No.
There's an interesting little story that Einstein developed an irritating habit for a short while of saying, what time does the station leave this train? And his meaning was that you simply can't tell the difference if the train is moving or if the rest of the world is moving underneath you. It just happens to be easier to get everybody to agree that the train is moving and the world isn't. But there's no basis in physics for doing that.
That's the thing about relativity. You've got to think about how one thing moves relative to another. Oh, God.
At the moment, I'm travelling at about 600 miles an hour relative to the ground. But it really doesn't feel like I'm moving. Everything behaves the same as if I was stationary. Well, that's because we're travelling at a constant speed. Now, the only way I can tell if I'm moving is by looking out of the window. But that would still look the same if the ground was moving and I was sitting still.
Exactly the same is true with the athlete running down the track. An athlete running nearly at the speed of light, zooming along, says, oh look, I'm staying still and all these people are hurtling past me at nearly the speed of the light backwards. So we look at the athlete, see, hey, he's moving really quickly, time is different for him. Athlete looks at us and says, hey, they're moving really quickly, time is different for them. And it's exactly the same for both of us.
Relativity says that who's moving depends on your point of view. So time depends on your point of view too. It's relative. Time is different for everyone. Absolute common time doesn't exist.
What Einstein had done was overthrow for good the old Newtonian idea that time is absolute. It turns out that we can, in fact, play with time, speed it up and slow it down.
But there's more. Relativity says that movement changes space as well. If I see Chris running along, because he's moving so fast, his space is compacted. He becomes all tall and thin and sort of squashed up. Time and space are connected. They're part of the same thing.
Einstein's genius was to say the two things, space and time, change together in just exactly the right way so that the speed of light is always the same, no matter how you measure it. And he said, the thing that's magic, the thing that's constant for everybody is not time, which has led to all these problems. Time is just something. The thing that is constant is the speed of light.
Einstein's genius was in connecting up various pieces of experimental and theoretical evidence and coming up with a whole revolutionary new way of viewing reality itself.
Reality, according to Einstein, says that space and time are elastic and connected. Don't think space, don't think time, think space-time. That's what they mean on Star Trek when they talk about the space-time continuum. Time is the fourth dimension.
We could no longer talk about living in three-dimensional space with time running by externally, but rather time had to be treated as a fourth dimension, and we really had to be talking about four-dimensional space-time because of the way time and space are mixed up.
We now know that time is just part of the space in which we live. We even call it space-time. The word time doesn't actually exist in physics in that sense. And so time is just something that is part of the way the universe holds itself together and is one of those things that we measure. It is a little different than all the rest of space because it's not so easy to move backwards in it. But other than that, it's just another thing, just like up and down.
We can talk about the whole totality of existence, of reality, being in a four-dimensional block, in the same way that a cube has three dimensions of length, breadth, and height. So if we add time as the fourth dimension, we can think of a four-dimensional block, which is the whole universe, with time as another axis in some other fourth dimension, which we can never appreciate, because after all, our brains are three-dimensional, so we could never appreciate the fourth dimension.
A map, when you unfold it, is two-dimensional. Add another dimension and you get the space we're all used to. But to get a full picture of reality, you need to add yet another dimension, time.
I like to call this the timescape. We're used to the notion of the landscape, and you can make a map of the landscape, you unfold it, there it all is. The whole landscape is sitting before you on your desk. Well, in relativity, you have to take into account time as well, and time is like another dimension of space, and you can unroll a four-dimensional map, and there it is. The whole of space-time simply exists as an entity. The timescape is there, as it were, all at once.
The universe becomes a strange four-dimensional block. In this block universe, the whole of time stretches along a line, with the past at one end and the future at the other. The past is behind me. I can never go back there. And the future is in front, way out in front. And that's the way I've got to go. Somehow all time is here already. It's a pretty odd idea, isn't it?
I can understand all time is now.
Can you?
Yeah.
Well, all time exists at this...
Yeah. So there's no... Yeah, I can understand that. Because if you stood outside of time and you looked at eternity...
You'd see all of it.
All you see is... Yeah, so that's the idea.
Yeah.
If we take the idea of the block universe literally, that all times coexist, then it means that our time now is no more special than any others. My young children, as far as I'm concerned, are children. They're not adults, they're not old-aged yet, that time hasn't happened yet. But in the block universe, all times coexist. Times before we were born, times after we die. And so each person's lifetime is all there, laid out there in the block universe.
If I was in an airplane, looking at a parade, and you was at the beginning of the parade, and someone was at the end of the parade, I see all the parade as now.
Yeah.
But if I come down from the airplane and come into the parade, I'll see you at the beginning and I won't see the end.
Yeah.
That is time.
Yeah.
I can understand that one.
It's weird, though, isn't it?
The debate about the nature of time has been raging for hundreds of years among theologians and philosophers. The Western religions believe in a God who exists somehow outside of our space and time. So according to God, all times, past, present and future, coexist. In physics, the only difference is that we talk about the whole of the universe existing together, and if there were an observer outside the universe, they would see the whole of time static. But of course, the whole of space and time is everything. The universe is everything. There is no outside to the universe. And therefore, you can think of it as an abstract concept that is useful from a mathematical, theoretical point of view, but maybe we shouldn't take it literally.
For better or worse, I'm stuck inside the universe. I can't see time stretched out before me like I can with space. But we all move through time. One moment follows another. The passage of time is common sense for us, but surprisingly hard for physics to explain.
I don't know why we perceive time to go by. Maybe there's something missing in the laws of physics. Maybe one day we'll discover the missing ingredient to put into the equations of physics that will give us an indication as to why we perceive time to go by. Maybe it is all just an illusion, but it's something that we haven't understood yet.
Imagine that the last 1,000 years took place in just one day. At daybreak, these remarkable figures appeared on Easter Island. Before breakfast, Edward the Confessor had built Westminster Abbey.
One of Einstein's most famous utterances is that the past, present and future are only illusions, however persistent. What did he mean by that? Because surely there's nothing more obvious to us in daily life than the existence of a now, of a present moment, and the future, which is sort of nebulous and not yet come into existence, whereas the past has slipped out of existence.
Logie Baird invented television in time for the evening news, and in the few minutes before bedtime, we've seen a man on the moon, the fall of the Berlin Wall, and the end of apartheid.
To believe that the past and the future coexist with the present implies that the future is already out there, and the past is still being enacted out there somewhere as well. And so there is no present moment. Our now is no different, no more special than any other time in the past and the future. And I think that's what we find too difficult to swallow, really.
Imagine what we can do tomorrow.
At the moment, physics does have its limitations when it comes to describing time, but it's remarkable what it can do. It's time for general relativity. Special relativity describes how speed slows down time. But if you really want to understand time and space, you've got to include gravity. Everyone knows things fall because of gravity. It's what holds the universe together. Wherever gravity operates, time slows down. The more powerful the gravity, the greater the effect. So the lower down I go, the slower my time goes compared to time up there. That's general relativity.
We don't notice how gravity changes time because it's such a tiny, small effect in everyday life. But the intense gravity around massive objects like stars and planets distorts not only time, but space as well. Remember, you've got to think space-time.
Einstein described gravity as a curvature of space and time. Now, very soon after he developed general relativity, he applied it to the whole universe. He applied his equations to try and describe the whole universe. It was that powerful. General relativity is even weirder than special relativity in what it says about time and what happens to time. The main conclusion is that time runs more slowly when we're inside a strong gravitational field. So if we go close to a massive star, then our time will run more slowly in the same way that it would if we were traveling close to the speed of light.
General relativity tied together the large-scale properties of space with gravity and showed that although we think of space-time as this big, smooth, uniform structure in which we live, actually it can be buckled and bent by matter, by gravity. And general relativity explains the large-scale structure, the curvature and the buckling and the twisting of space-time.
And what Einstein discovered was that the universe had to be unstable. It couldn't be static. The galaxies, which are the building blocks of the universe, had to be flying apart, or they had to be sort of moving together in the sort of reverse of an explosion.
Experiments tell us that the universe is still expanding after the Big Bang. But if there's enough matter out there, there might be enough gravity to stop the expansion and pull the universe back together. This big crunch might eventually be the end of everything, including time. Even though we won't be around to see it, physicists would love to know the ultimate fate of the universe.
I'm trying to understand the ultimate fate of the universe, and I'm doing it a mile underground down this mine. What we're trying to study is dark matter, and this ultimately determines the fate of the universe.
We know that there is a great big chunk of matter, of mass out there in the universe that we can't see. This is known as dark matter.
The strongest evidence for dark matter really comes from the dynamics of galaxies, and you can use the speed that these stars are rotating to calculate the mass of the galaxy. You then add up the stars that you can see and the dust that you can see, and you find that you only have 10% of the matter is visible to you. So 90% of the galaxy constitutes dark matter. And the question that physicists are trying to answer is, what is this 90%?
So it seems there's an awful lot of stuff out there we just can't see. Even though it's not visible, we think dark matter's there, otherwise there wouldn't be enough gravity to hold the galaxies together. But we don't know just how much mass there is in the universe. Perhaps enough to bring about the end of time.
If the mass of the universe is such that there's enough mass to gravitationally stop the expansion of the universe and bring it back together, then you have a big crunch, and space and time will stop. If there's not enough mass to do that, then the universe will continue to expand forever, and time will continue along with it. The latest theories of particle physics predict a new particle, generally called a WIMP, a weakly interacting massive particle. And it has the characteristics that, because so many of them were created in the Big Bang, that could constitute this huge fraction of the mass of the universe. The real problem trying to find dark matter is that your dark matter signal is being swamped by a lot of background radiation and cosmic rays. So you're looking for a very, very small signal against this cacophony of noise in the background. So we get away from the cosmic rays by going underground. We make our detectors from very, very pure material, so there's very low in uranium and thorium radioisotopes. And then we shield from the low levels of radioactivity in the rock using either lead and copper castles or water. We've been running at the Bulby mine since about 1990, And in that time, a lot of effort has gone into improving the detector systems, basically to improve the sensitivity. And we've now got to the point where the detectors are so sensitive that we see an anomalous signal. And by that I mean we're seeing a signal which we don't yet understand, and it doesn't match the expected profile of either the WIMP or the background interactions that we see around us.
One day, we might find the answer to the end of everything down the Bulby mine in Yorkshire. Or maybe one of the other experiments going on around the world will discover how much mass there really is missing from the universe. Meanwhile, the debate rumbles on. Will time ever come to an end? Or will it just go on forever?
What do you think happens at the end of the universe?
At the end?
Yeah. At the end of time, at the end of the universe, at the end of space, at the end of
Yeah.
time. What happens?
There are three classes of answer. One is that the universe actually stops. You have an end as well as a beginning, and the universe expands out from the start. It stops, it turns around, it falls back in, and it stops. And that's the end of it. You know, you've had your universe. You know, bad luck.
The big question we would like to know is, will it go on expanding forever, or will one day it sort of reach a maximum size and then begin to shrink again, perhaps ending up in a big crunch, which would be like the Big Bang in reverse. So whereas the Big Bang was the beginning of time, the Big Crunch would be the end of time. Literally, the whole show would go off the road.
Because it banged out with the big... Maybe it'll all go back in.
A sort of implosion?
Yeah, and implode down to a little nothing.
The next answer, and this is the one Einstein favoured, was the universe goes out and stops and just stays stopped and just sits there forever and you die of boredom. The third possibility, and this is the other interesting one, is that the universe just slows down but carries on expanding forever and ever and ever.
Rather than ending with a bang, it'll end with a whimper. The stars and galaxies will end up infinitely far apart, their nuclear fires will die out, the universe will become an incredibly dark, diluted and quite boring place.
The stop and die of boredom option is the one that is mathematically neatest and everybody would like to be the true answer. And in that case there is no end. Time goes on forever. Eventually all the stars will burn out, all the galaxies will be gone, the universe will be a profoundly boring place, but nonetheless it will be a profoundly boring place literally forever.
We could spend forever waiting for time to end. You know, it behaves in some very strange ways. Maybe it's not worth the wait.